Okay. So what the last exercise we were doing, or we were talking about capacitors in series and in parallel. And remembering that the series connection is this connection where we created sort of a chain between the elements. And there's basically three things that we were interested in circuits having to do with capacitors in charge. And these three things were capacitance, voltage, and charge for the elements. And these behaved a certain way for series elements. And so we had done this example where we've got three capacitors. Each of the capacitors has a certain capacitance, and these are connected to a power supply, in this case a 12-volt power supply. And we wanted to know what the charge was and what the different voltage was in each of the capacitors. And so of the three things we're talking about, the capacitance, the charge, and the voltage, these are going to behave differently in series and in parallel. So first off, we talked about the concept of the total or equivalent capacitance, which is basically I have three capacitors here. So instead of having the three capacitors with three individual values, if I were to substitute that with one capacitor that would have the same effect, what would that value be? And that's called the total or equivalent capacitance. And in that case, the total or equivalent capacitance for a parallel array is going to be what's called the reciprocal of the sum of the reciprocals. Okay, which means 1 divided by the total or equivalent capacity is going to be the sum of the reciprocals, or 1 divided by each of the capacitors. That's the sum of the inverse of the reciprocal of the sum of the reciprocals model. And therefore we can find the total capacitance for those three capacitors. And again, what does that mean? It means that I have three capacitors with three values. What would be the value of capacitance I would substitute if I were to have just one capacitor? Okay. And we mentioned something last class that there might be a question in the exam. If I have a parallel array of capacitors, n capacitors, and each of them has its value, what did we say about the total capacitance? Is it going to be larger or smaller than each of the values for a parallel array? It's going to be smaller. So if I had 2, 3, 4, 20 capacitors connected in parallel, and each of them has their individual value, if I calculate the total or equivalent capacitance of that array, it's going to be smaller.
But is it parallel? Series is not.
No, parallel, the total or equivalent capacitance of a parallel array is going to be smaller than individual.
But that one is series, no?
I'm sorry. Thank you. Yeah, I'm mixing it up with the resistors. Rewind. We're talking about series capacitors here. Thank you. In series capacitance, the total capacitance is going to be smaller than individual. Parallel is the other way. Even I get confused sometimes because when we see resistance, it's going to be the other way around, and inductance is also going to be the other way. So, but thank you for the clear up there.
It's smaller than individual.
Than the individual ones. And that way I can make a smaller capacitance value from an array of capacitors.
And that's because the voltage is spread out.
That's the other thing, Ricardo, that's important. The voltage is going to be distributed. So if I have a total voltage of whatever value, that voltage is going to be distributed proportionally among the elements. That is always going to happen in a series connection of any type of component. So the total voltage is distributed. And therefore, when we calculated the voltages, we saw that each of the elements is going to have a voltage. And the sum of all of them has to give me the total voltage of the power supply. That's because the voltage or the power supply is providing energy. And again, I'm not creating or destroying energy, I'm distributing it. Okay. The other important thing here that I'd like to mention is that when we're talking about electrical or electronic components, one way or a general way to classify electrical or electronic components with regards to energy is that there's two types, passive and active. A passive element is one that's always going to absorb or attract energy. An active element is an element that can provide energy. So a power supply is always going to be an active element. A battery is an active element. It's something that's trying to give me energy to do something. Okay. In this case, and for all of the components we're going to see in this course, a capacitor is a passive element. It's going to store charge. It's going to store energy. It's not going to create it. And therefore, the logic here is that if I have a system or a circuit, the sum of the active elements has to be equal to the sum of the passive elements. Okay? Because we're not creating or destroying, we're just distributing. So if the power supply is 12 volts, and that is distributed in the array, and the capacitors are passive elements, then that has to be distributed equally. And the sum of the passive elements has to give us the active. And the last thing is that for an array that's going to be a series array, the charge is going to be the same. There's going to be just one charge, one total charge that we're going to be working. At the end, when we finish up this section, we're going to do kind of like a summary of these points, and we're going to write them down to remember them, so we can differentiate the series and the parallel. Okay, so that's this situation where we're just talking about the series connection. By the way, there's two solutions here. This is the procedure we did in class. And there's also another procedure here that's going to be included in the PowerPoint, which is the same procedure, but just without my ugly writing. There's one thing that I noticed, and I'm not sure where the typo is. I'll let you guys solve that mystery. The only value that's different, and I think it's a typo on one of the slides, it says this value. Here we wrote down 6.54, and the one I have is 6.45. So yeah, the decimals were switched. So
There's not a typo because in the top it says 5.45, in the bottom it says 6.54.
no, but this is the result. This is the result of this product. So either this one is switched or the other one, but it's within the same range. I think the rest of the values are. I think the other one has, yeah.
The calculations and we got those values.
Yeah, so maybe I'm going to verify that. If the typo is here, I'll just correct this one. So the only one that was different is this one. So maybe this is 54. I'm gonna double check that. But the procedures are the same. Now let's talk about the parallel array. Now the parallel is going to behave a bit differently than the series. In the case of a parallel array, the voltage is going to be the same. If I have a parallel array, the voltage is shared. So the voltage is going to be the same across all of the elements. The voltage is going to be the same. The charge is going to be different in each of the charge is going to be different in each of the elements. And the capacitance is the total or equivalent capacitance is also calculated differently. It's actually much more simple than the series array. The total capacitance is simply going to be adding up the individual capacitances. And so, assuming that I connect the battery here, since it's in parallel, the voltages are going to be the same. It's going to be the same voltage. The charges are going to be different, and the total capacitance for a parallel array is simply going to be adding the individual capacitance. And I'm just going to add them up.
Same voltage, but different.
The charge is going to be different. So that's in the relationship we have between charge, voltage, and capacitance for the series. Charge is the same, voltage distributed. For the parallel, it's the other way around. Voltage the same, charge distributed. So
We saw these on TikTok
on
yeah,
TikTok.
high school. No.
Oh, I thought you said,
Different.
I thought you said TikTok. I'm like, I don't have. Yeah, probably. I don't know how many of you
On
took
FEMA,
like electricity
yeah.
and magnetism course. Usually, depending on the high school you come from, usually the electricity and magnetism course. Yeah, if you're in math.
Amador gave us,
Oh, I know him. He's a good guy. I know him. He's a good guy. Or am I confusing him? No, I'm confusing him. I'm confusing him. No, yeah, but yes.
No,
Now, depending on your high school program, in some high schools that have a sort of a math and physics major, the structure of the math physics major is very similar to engineering. So you usually take 1 or 2 calculus courses, and you usually take statics, dynamics, and physics, or statics and dynamics are combined. So it's probable that you already saw some of this. So it's a refresher. And actually, there's something weird about this course that we're going to see in learning module number 3. I'm going to go very quickly in learning module number 3 in the next one, because you guys are going to take the industrial electronics course next semester. And actually, the first unit of that course is the 3rd unit of this course. So it's duplicated. Why is it duplicated? Because you are the only academic program that takes, well, no. Yeah, you're the only academic program that has an industrial electronics course. And so we don't need to go that deep in this course. We're going to go deeper in the next semester. But yeah, maybe you saw this, some of this in any of your electricity and magnetism classes. I've taught that course for the global program since the global program began. Yeah, I taught it 3 times. The first one. Yeah, 3 times. No, I taught it every year. So I'm hoping to teach it. It's a very fun, I like the course a lot. It's a more practical course in this one because here we're looking at the electricity and magnetism course is more, it's a physics course. So it's more focused on the physics part, but the industrial electronics course is more focused on the application part. And if we could have face-to-face next, so if this continues next year, it's going to be even cooler because we're going to be able to do the lab exercises in the lab. And be able to expand on that, because the last time that the course was taught, the lab part was virtual. It's not virtual. We gave the students some kits so they can work at home. But still, there could have been some applications that we could have done that we need some lab equipment over here to do them. And so if we get to do that, it's going to actually be fun, and you guys are going to be able to do a project, which is going to be interesting. So let's hope that this continues for next semester.
Professor, I was with Marisa at her house and she had the.
Oh, and Marisa, that was last year.
Last semester.
Last semester, yeah.
And she was doing the homework with Rene and Alex, and they told me that it was really hard.
Yeah, well, I know, I by the way, any comment I make, I want to mention and stress that I'm really fond of, I love all of the industrial global program students and everything, but I know them. So I know Marisa got, I know, or I had the impression that Marisa got really stressed about the lab exercises. And I understand that because it's basically you're trying to do a circuit and there's somebody on the screen trying to explain to you how to do that. And I understand how that can be a little bit stressful. So I noticed on the screen that Marisa was, you know, the Zoom breakouts. Whenever that team was together and I jumped into the breakout, like I do with you guys, it's like, oh, professor's here. Yeah, I had some doubts about, and so I noticed that some of them were a bit stressed about that. I think part of the thing about it being hard, I think, was the distance part, because if you're working on something practical and you're trying to do it via Zoom, it's not that easy. So let's hope that we can do it face to face here. Some of the topics might have been hard, but I don't think harder than what we're going to be seeing here. So that's going to be fun if we get to that point.
But it was cool to be able to give them the kits, so at least they had something practical to do during the pandemic, because in other situations, we wouldn't have been able to do that. Let's hope we can do it next year. So the total capacitance in this case is going to be simply adding up the capacitances of each of the individual components. So therefore, the inverse situation occurs here. The total capacitance for a parallel array is always going to be larger than the individual capacitances because we're adding them up. So I can create a larger effect by putting things in a parallel array. And they're all in exchange right now. I talked to them, by the way, after you reminded me that, I sent messages to all of them, so that all of them are in Europe.
Yes, you want mine.
They're all in Switzerland.
They're in Switzerland? Oh, wow. Do you know which part? But do you know in which part of Switzerland that
They
they're?
went Bern.
Bern.
They had not traveled.
Yeah, Switzerland is very beautiful.
Yes.
Not on, I actually left a bag of them here with 2 Oreos last class. I don't have any more right now. I'm really sorry. Listen, I was thinking about bringing cookies each class, but my budget wasn't going to be able to support that. So you will be getting goodies periodically, but not necessarily every class. Dr. Shank, I think, when he teaches a workshop, no, you didn't get the physical workshop, but he brings M&Ms to remember the manning machine thing. So yeah, we'll be doing that. We're going to be doing stuff in each unit to remember things, but not necessarily the. I'm gonna, if you guys want to, because of the exchange in Switzerland and all that, maybe next week we can take a few minutes so I can show you some pictures of Europe, of different countries in Europe when I was over there. And Switzerland I fell in love with Switzerland, and it's such a diverse country. It's a country that mixes the German part with the French part with the Italian part. So Bern is more towards a certain section of Switzerland, and there's Zurich, and there's Geneva. It's such a beautiful place. So if they're over there, then that's so cool. Okay, let's work on let's work on this. Oh, when I show you the pictures, I'll tell you the anecdote about how an alumni friend of mine, who's a cybernetic electronics alumni, he studied in here at Cetis. We almost got kicked out of the United Nations. So that was fun. That he's getting kicked out of the United Nations. For okay, so let's talk about this situation here. Now we've got 3 capacitors that are arranged in parallel. And we've got, oh, by the way, with regards to terminology, Alejandra, you have to do this sort of supply and demand thing. So Yesenia wanted cookies, you have cookies, you need to tell her. So how much do you really want those cookies, Yesenia? And then you're going to have to.
Can you give me one?
Professor.
Nobody, well, me and my immediate family don't know anyone else with the same last name and having like funnel. And we know German because of our, and we know German because of our grandpa. And from Jose DC and Switzerland, you send me a picture of an ice cream shop and chocolateria.
Funnel. That's so cool.
And Connie just walking down the street.
Because it's probably European origin, right?
German.
Yeah, but talking about the trip that we made to Florida where we went to Cape Canaveral, we went to Disney over there, and in the boardwalk, there was a Sosa cigar company, actually. Sosa cigar. It was like Oh, and by the way, pay it forward. Alejandra's being generous enough
Yeah.
in sharing her cookies. So next time that you bring cookies or bring something, offer it to Alejandra. She's being gracious enough for that.
I can make brownies one day.
We used to
Yes.
do
We would love that.
Or 2
Yeah.
days.
And I think, I know that Alejandra's doing it out of a good place in her heart where she wants to share things. Not like my daughter, when my daughter shares something, if my daughter were in this situation, and any of you were, I would say, Sarah, should you give me a cookie? She would be like, she would eat a few, and then we'd have a cookie and say, this is the one I don't want. There you go. So it's something we need to work on with Sarah, sharing, because right now we're having challenges with that. So thank you, Alejandra, for sharing your cookies with the group. So now we have this situation with your capacitor. Now, again, there are things we're going to be seeing in circuits that we sort of identify because we can find different terminology and different symbology, but everything is the same. So first, we already mentioned that when we see this arrow here, and the I, what did the I mean? Current. And that just means that whenever I'm connecting the power supply to a circuit, a current is generated. Right now, for this learning module, we really don't care about current. We haven't talked about it yet, but that's what this I means, okay? Now, the other thing is notice that there's an A and a B. This A and B are just 2 points in the circuit, and these lines here means that between these points, we're connecting a battery, a 12-volt battery. Now, we could do it this way. That's one way of representing the circuit. Or we could actually literally draw the battery there if we wanted to. And there's different symbols there for battery. So another thing is that this could be here, and we could have the symbol for a battery. This is the symbol for a 12-volt, for a battery, I'm sorry. The long line is the positive side and the short line is the negative. It's very similar to the symbol of a capacitor. So that's another way in which we could represent the battery. Or if we just want to represent that there's a voltage source being connected there, then we can do it like it is here in the circuit. We could just have the 2 points and these lines saying that between those 2 points, there's a 12-volt power. What do we want to find? We want to find the total capacitance charge and the total capacitance of the circuit, or equivalent capacitance. I think the more correct term is equivalent. Total is fine, but equivalent is more descriptive because, but anyway, something that is a common mistake in the exam when we're talking about capacitors and resistors and other stuff is when I ask you about the equivalent, explain what equivalent capacitance is. And one of the responses that I usually mark wrong is when you answer, it's the sum of the capacitances in a circuit. It's the sum or parallel. It's not the sum or the arithmetic sum for series. We saw that it's a reciprocal. So the correct answer to what is the equivalent or total capacitance or whatever would be the way I mentioned it. It's the equivalent value for a group or an array of capacitors that provides the same effect. It's the equivalent value of capacitance of a group of capacitors, or you can say group, you can say array of capacitors that provides the same effect. It's the equivalent value of a group or array of capacitors that provides the same effect. Yeah, so a typical question in the first section is what is equivalent capacitance? That's probably going to be a question. Remember that in the exams, there's 3 sections. The first section is direct theory. That's going to be a typical question. By the way, again, not for this exam, for the second exam. This exam is described as yes. The equivalent value
It is the equivalent value of capacitance of a
Of capacitance, the equivalent value of capacitance of a group or array of capacitors.
Of capacity.
Capacitors that provides the same effect.
The same effect.
The same effect. And so let's work on this. Let's work on this problem. Okay, so let's work on this. I'm gonna work here on the desk with the writing. I didn't bring the easel because I think I can still see all of you guys if I'm sitting here. And people think I'm protesting when I walk around with that thing, and it's not cool. So the first thing that we're going to calculate, or that we want to find, let's find the total or the equivalent capacitance for this array. And so the equivalent capacitance in this case, let me just quickly check my color coding here because I want to use the same blue. The equivalent capacitance for this circuit is going to be given by, let's call it C total. Because they're in parallel, then I just need to simply add up the capacitances. So it's going to be C1 plus C2 plus C3, and that's going to be a direct addition. So the total capacitance is going to be equal to, remember this U means micro, which is times 10 to the minus 6. So it's going to be 0.1 times 10 to the minus 6 farads plus 0.2 times 10 to the minus 6 farads plus 0.3 times 10 to the minus 6 farads. And remembering that farads are the units for capacitance. And so the total capacitance then is 0.1 plus 0.2 plus 0.3. We're going to have 0.6, correct, times 10 to the minus 6 farads, which is equivalent. We could also say that this is 0.6 microfarads. It's 6? No, no, it's oh, yeah, well, 6 to the minus 7 is it's the same as 0.6 to the minus 6.
Yes.
Yeah, it's yeah. So basically, and yet we're adding, so it's the same value. So you got, and yeah, you got 6 to the minus 7, right? So 6 to the minus 7 is the same as, so 6 times 10 to the minus 7 is the same as 0.6 to the minus 6. So if I want to turn the 6 into a 7, I need to move the dot this way. Okay, so it would be equivalent. Is that okay?
Yes.
Yeah, that's good. A colleague of mine, we were joking about that because we come from a different, we were both born in the same year in 1975. So we had very different educational experiences than you guys had. We have very different teachers as well. And we were joking about that not I'm saying that's gonna happen here, but we were joking about that
Right now, we have to kind of deal with situations where we say, well, 2 + 2 is 4. And we're expecting somebody to say, no, I don't think so, it's 6. Well, no, it's 4. Well, that's your opinion. My opinion is that it's 6. Yeah, but it's 4. Well, that's your opinion, Professor. But for me, it's 6. Yeah, but it's not 6. Well, I respect your opinion, Professor, but it's 6. And so, yeah, it's gonna be, it's like mine, so you got a different result, but actually you have to respect that, I have a different perspective. And that's respectful. There's a video you can, I saw it on 9 day. That's kind of the different perspectives of how different generations react. But that's not necessarily something negative, because I think speaking out is also important, because when we were studying, we had kind of a structure where we couldn't interact the same way with the professor. So even if the professor was wrong, and we had situations where the professor was wrong, we can like kind of raise our hands and say, Professor, you're wrong, because that was not kind of allowed.
So in the exams, if that professor check you wrong,
We had a couple of situations. I remember particularly in 8th semester, I remember a law class that we had. That, yeah, I wasn't very happy with the results of the exams. But it was a law professor, and I remember that it was kind of like cross-examining you. And so even if the professor, so back, the education has changed. So before it was like the professor is always going to be right, and the dominion of the class is always going to be of the professor. So your role as a student, you only have to be sitting there taking notes and saying yes, yes, yes. And so there was no interaction. It was actually not that dramatic. We had a lot of professors that we engaged with and all that, and we talked to, and they were very nice. But it was a different dynamic. I don't think it was as open as it is right now, where a student can say, no, I don't agree, or you're wrong. Or like Viviana right now, it's like, you're saying things the other way around. I'm like, yeah, boy, I can't say things the other way around. Series of parallel, I'm mixing them up. Thank you for that. And maybe in another situation, I was like, no, I am right. And then in the exam, you're going to be studying, and like, it's confusing. He was wrong. So, yeah, we don't even want to go there right now. But so that's the total capacitance. And notice that, again, for a parallel array, the total capacitance is always going to be larger than the individual capacitance that we have. What do we know about the situation in a parallel array? If any of you need to step out, go to the bathroom, or just make a sign, you may do that. What we know in a parallel array is that the voltages are going to be the same. So there's going to be a total voltage. And what's the value of the total voltage in the circuit? 12. It's going to be the 12 volts. That's what's being provided by the power supply. And that voltage is going to be the same in each of the elements. Do you have stuff in your, do you have stuff that has batteries in it that you use in your home or whatever? Control, calculators, etc. I'm gonna ask you to do this sort of exercise. And maybe next week I'm gonna ask if some of you wants to share. But for any of the device, pick 3 devices that need batteries. Let's say your calculator, your remote control, and something else, your mouse, for example. And open the battery compartment and look at how the batteries are connected. And try to identify if the batteries are connected in series or in parallel. When you open something that has a battery compartment, notice that there's not all of the batteries are always connected the same in the device. Have you noticed that?
Usually in series.
Some for the alternators like this.
Yeah, there's different ways in which the batteries are connected in the device. Let's see if I don't break my mouse, and I can show you here with this one. So there's different ways in which the batteries are connected. So usually, for example, what is the voltage of a let's see if you guys know. I was joking with my wife. This is being recorded, I need to pause this. Or else I'm gonna get in trouble. Yeah. Resume. Okay, so now we're going to be looking for the charge. And so how can I find the charge? Well, I know that the color here. I know that first I'm gonna try to find the total charge. And so the total charge is going to be equal to the total capacitance times the total voltage. That's the total charge that we have in the circuit. And we know that that charge in the end is going to be distributed. So the total charge is going to be the total capacitance, which is 0.6 times 10 to the minus 6 farads, multiplied by the total voltage, which is 12 volts. And so what is the total charge?
7.2 times 10 to the minus
7.2 times 10 to the minus 6 coulombs, or 7.2 microcoulombs. 7.2 microcoulombs. And that makes sense because we're talking about microfarads, microcoulombs makes sense. And then we can find the individual charges. And how do we find the individual charges? Well, Q1 is going to be equal to C1 times V1, which we know is the total voltage. And so it's going to be 0.1 times 10 to the minus 6 farads multiplied by 12. We know that Q2 is going to be C2 times V2. This is going to be 0.2 times 10 to the minus 6 farads multiplied by 12 volts. And Q3 is going to be C3 times V3, which would be 0.3 times 10 to the minus 6 farads times 12 volts. So give me those three values, please. You lost your calculator? Oh, you lost it as well? What's that mean?
I had to.
You had two and you lost them. Oh.
I had one in case I lost the first.
And that backup plan did not work out as we thought it would. Did you lose them here in Cetis?
I don't know. I lost.
Check maybe on there's a lost and found
I
here on
think
the
I have
bottom.
one, at least one of them.
Okay, must be somewhere at home. This one should be
1.2 times 10 to the minus 6.
yeah. Columns. This one should be double that, which would be 2.4, right? The only difference between writing in PowerPoint and writing in Zoom is that something curious that I had not noticed, and this would be 3.6, right? Something that I had not noticed with this tablet that I have is that in Zoom, the writing doesn't depend on how strong I'm writing. And here in PowerPoint, if I press down, it's going to be thicker than if I write lightly. And that's interesting. Technology. What can we notice here? If I add these, then I have to get the total charge, which would be the 7.2. Which is the total charge. Why? Because the total charge is distributed. Okay, questions with this one?
The voltage, the total voltage is 12.
Uh-huh. The voltage that is the total voltage, and the voltage in each of the elements is going to be 12. Which one? I'm sorry. Yeah, that's a funky 6. Let me.
Como eran hamburguesas de pasta.
Question with this one. We keep talking about food.
I'm hungry.
Yeah, me too. Me too. Okay.
Pues eso,
Okay, let's talk about summary over here, or else your stomachs are gonna explode.
My daughter eats a complete 8-piece pepperoni pizza. Like it's nothing.
and she's so.
She's 6 and she's small. She's not. She's very tiny. We literally buy a medium 8-piece pizza, and we have it there, and we start eating, and suddenly my wife goes to work, and I go to do something, and then it's like my wife, oh, there's no more pizza. Jorge ate the last piece, and I'm like, oh, there's no more pizza. Maggie ate the last piece, and we're like, we didn't eat any pizza. And and she's curious because she doesn't eat the sides. So she'll eat the complete pizza, but she's like healthy. And she doesn't eat the sides of the. She wants to be healthy. She eats the.
We went out and I told me, can I get a piece of your pizza? Okay, she took literally just the side.
Just the side. Well, the side with some marinara sauce is really good.
No, just the side.
Just the side, nothing else. Yeah, but I don't know where it goes. The thing I can say is that my daughter has a lot of energy, so I think that's how she burns calories. But yeah, I mean, she's this small and she's 6 years old and thin, and she can eat a complete pizza and still be hungry. And my son, he is chubby. He is this close to being baby obese. They told us at the daycare, they told us that he's on the edge of being baby obese, but he's happy about it, and he's cute.
He will not be actually, because.
I hope not, because the way he's going, I don't know. I don't know if that's going to.
He used to be on the border of obesity.
And they turn out skinny.
And they end up skinny, right?
My brother.
No,
Muy perfecto, ¿no? Hasta ahora son 2 kilos de O pero era un poco tan chiquito.
Es un poco del tamaño de 3 kilos.
Sí, yo también, o sea, está chiquito. Tiene que pesar 10 y pesar 15.
well, my son is 6 months old. He just turned 6 months on Sunday, and he's 8.7 kilograms for 6 months. That's a complicated question that I need to ask my wife, because he's not wearing baby clothes of his size. I think we're buying 9 months right now, 6 to 9. So if I say my son is 6 months old and we buy a 6 months old onesie, he's gonna be like those wrestlers that have the kind of the stretch things out. It doesn't fit. But he's happy, and we were.
That's what counts.
Yeah, I was gonna show you a video, but I'm not gonna be able to send it. No, but I can't show it in the.
And well, the baby's parents are like very tall and this. So when he was like,
Yes.
6 months old, when he was 6 months old, he used
Okay, so let's do this summary to finish up. So what's the difference between series and parallel? Just so to kind of summarize and have a very quick view of how they differentiate themselves. First off, in series, the charge is going to be the same, okay? And that's the thing. So Q is the same. And by the way, when we say the same or distributed, it means that we have n amount of elements. We have 2, 3, 4, 5, 6, whatever. The charge is the same. In parallel, the charge is distributed. Okay. In series, or in parallel rather, the voltage is the same. And in series, the voltage is going to be distributed. And lastly, the capacitance in series, it's a reciprocal. 1 divided by the total capacitance is going to be, I'm going to do it in mathematical terms, but it's going to be the sum of the reciprocals. In parallel, the total capacitance is going to be equal to the sum of each of the capacitances directly. And lastly, what we can also say is that in series, the total capacitance is smaller than the individual capacitances. Looks like it says individual. And in parallel, the total capacitance is going to be larger than the individual capacitance. That's kind of like the summary of series and parallel for capacitors.
next unit where we talk about resistances and currents, some of that is gonna stay the same. Actually, these two are gonna be related. This is the one that's gonna be inverted. But this is kind of like a summary of the of what we've seen up to this point. And the next exercise is, yes,
I have a question.
yes.
When you say total capacitance larger than individual capacitance or capacitors.
Either way, it's the same. So it's gonna be, but it is plural, meaning the total capacitance is gonna be smaller than each of the individual capacitances or capacitors. Okay, and here it's gonna be larger. So like the example we saw, if we have 3 capacitors in series, each of them has its value, and we calculate the total or equivalent capacitance, but that's gonna be smaller than the individual. And in parallel, it's gonna be the other way around, it's gonna be larger. So this is kind of a summary of what we saw. What we're gonna be seeing next week on Wednesday, we're on class on Monday, we're gonna be doing some exercises, mixed exercises. So